A very good morning to everyone. I, Pallavi Thapre, on behalf of Safe CRNTS, IIT Bombay, take this opportunity to welcome you all to today's webinar on laser Raman imaging, titled Correlative Microscopic Technique, a tool for advanced material characterization. At the outset, I will provide overview of SAFE, brief introduction of today's speaker, Mr. Hitesh Mamge, followed by his presentation on the topic, and the last question and answer session. I request everyone to post their question with their name in the question and answer box, which will be answered towards the end of the session. Sophisticated Analytical Instrument Facility, also known as SAFE, which was inaugurated by our late ex-Prime Minister Shri Morarji Desai in 1976. Project CRNTS started in 2006 with initial funding from DST, and in 2008, SAFE and CRNTS got merged under one umbrella headed by one in charge. Professor Anil Kotyantare is currently heading our department. We have 16 major equipment under SAFE and 5 major equipment under CRNTS. CRNTS, being the academic wing, also has PhD program. We have more than 80 students associated by 65 faculty members of other departments. Financial year during 2018 and 19, we have more than 2,000 users and more than 20,000 samples were analyzed. Department of Science and Technology has set up sophisticated analytical instrument facility in different parts of India. The main objective to set up this facility were to provide guidance in acquisition of data by using sophisticated instruments. SAFE IIT Bombay has several analytical instruments which provide measurement services to IIT Bombay users and the users from other colleges, universities, national laboratories and industries as well. DST has provided fund for the following instruments. These are the instruments which comes under central facility funded by IIT Bombay. Dr. Mayuri Gandhi is in charge of this laser Raman spectroscopy, which is in-house at SAFE IIT Bombay. To know more details of SAFE CRNTS, please visit our website, that is safe.iitb.ac.in. It's my pleasure to inform you all that in spite of 17 SAFE funded by DST, we have a user and researcher coming to our SAFE from all over India and Nepal. SAFE is not just a center for research, but we also encourage people to visit our center to help them understand and demonstrate how our facility works. We also encourage visitors from industries and universities as well. We have a LinkedIn page of SAFE IIT Bombay and we would be happy to connect with you on LinkedIn. We have in all lineup 12 different webinars on different topics. You can get the details of these upcoming webinars on our website and LinkedIn page also. I once again taking this opportunity of thanking everyone for joining today's webinar, and all our team members would be happy to welcome you at SAFE CRNTS, your research and development work. Now it's my pleasure to welcome Mr. Hitesh Mamge. He is currently associated with Vitech as an application scientist. Mr. Hitesh Mamge received his undergraduate degree from Pune University from the Department of Electrical Engineering in 2005 and completed his post-graduation degree from University of Leeds from the Department of Chemistry in 2006. He joined Vitech as an application scientist in 2009. His primary interest areas are in instrumentation in the field of atomic force microscopy, scanning near field optical microscopy and optical spectroscopy. Now I request Mr. Hitesh Mamge to present his slide to everyone. Over to you, sir.
Good morning, everybody. My name is Hitesh Mamge. Together with Mr. Satish Kumar, Dr. Jamie James, and Mr. Matthias Kress, that means the contribution is from everybody. We'll be presenting correlative microscopy. And the whole idea of correlative microscopy is that you need to combine all the techniques that are possible that complement each other in order to give you a better understanding of your sample, and also apply, let's say, at a later stage, if somebody is interested in machine learning, artificial intelligence, they can apply those techniques to data analysis in order to generate these the results in a much better fashion than a human could ever achieve. So multimodal imaging. Now, if I am here, so in multimodal imaging, the main criteria is that you should be able to take images of complementary nature from the same location. Now, here, one second, so what we have is my talk is revolved around optical microscopy and spectroscopic techniques combination, then a little bit of electron microscopy, optical microscopy, and confocal microscopy combinations, and also a combination of confocal and optical along with scanning near field optical microscopy. And I'll touch upon a few new fields, for example, combining Raman spectroscopy with mass spec, or combining Raman with IR imaging, those kind of technologies in the end, if time permits. So this is the outline. So we have, yeah. So base is around optical microscopy, and optical microscopy is something that a lot of people consider as a basic form of microscopy, nothing too unique or something like that. But when they think of optical microscopy, we are thinking only the bright field domain, not in the dark field domain, DIC, phase contrast, fluorescence, polarized light microscopy. And I'll give you a few examples of all of these. From there, we'll jump into confocal, because that's the most obvious method to increase resolution. And confocal is only a technique to increase the resolution for all these techniques and add in spectroscopic information also. All these information that you see here is spectroscopic. Only white light is just reflected light microscopy. Then we'll do a combination with scanning electron microscopy and scanning probe microscopy. I haven't detailed this too much. It's atomic force microscopy and related techniques. I won't touch into optical profilometry right now, but we'll touch upon IR imaging and mass spec a little bit, and also what are the challenges which we have there. Now, a fine example of correlative microscopy is, for example, this particular sample, which is kimberlite samples, which are generally generated, kimberlite rock formations are generally generated like 150 kilometers under the Earth's surface. And from there, they keep on traveling upwards. And people have been looking at these fluid inclusions for a very long time to look at the carbonate component within them, because these are good source for diamond and everything. So here what we see is optical microscopy, wherein it's a transmitted light optical microscopy. Light is put from the bottom and viewing is from the top. You can easily see all these samples. For example, number 1 is over here, and this number 1 is also over here in polarized light microscopy. So the contrast increases to a certain extent with polarized light microscopy. And then when you perform Raman spectroscopy over the same point, you have reflected light microscopy, polarized light microscopy, and the Raman imaging all correlated with one another. And when you have Raman spectroscopy, you also get the spectral information. These are the spectral information from these samples, which gives you more information about the mineral content. Where is the carbonate, where is mica, where are other components in the sample. So this is generally what correlated microscopy is. And you'll have to take from this presentation whatever would be applicable to your field. It could be polarized light microscopy combined with fluorescence microscopy, confocal. It could be Raman spectroscopy combined with electron microscopy or with AFM or something like that. But I'll give you a complete picture. I've tried to keep away all commercial aspects of the instrumentation. Only my company logo is here. So, but apart from that, I've removed all marketing material, and it's only technical. So again, with correlative microscopy, we start with optical microscopy, and the most common technique with optical microscopy is bright field, a common microscope that you can purchase for $1.5 lakh, wherein you have a light source. The light source is collimated using a lens, and then using a beam splitter or a mirror, you transmit it to the sample, you illuminate the sample, and then you either look through a camera or you look through the observer, which is the eye. So it could go to the eye, it could go to the camera. Now, in two techniques in optical microscopy, which is bright field and dark field, the contrast changes, and that gives the operator a little more insight or contrast mechanism to be able to view his sample. Now, bright field is that what I explained earlier. When you have illumination, you shine it on the sample, it gets reflected, and that you see the sample. But in some cases, what you would want to do is the light which is reflected directly straight forward. This is something that we want to remove. So we put a black or an opaque circular disc in between. So light only coming from the edges would be visible. Now what it does is that on a planar surface, for example, this is a plane surface, light gets reflected back straight. So what you see is on an angular collection, you will not see planar surfaces, but what you see is small sample particles which are not easily visible with a bright field image. So those you see, and plus you get a different contrast mechanism on the sample itself. Now, Reinberg is just a dark field adaptation. Instead of putting a black or an opaque light blocking mechanism, he put in a filter. You can put a purple filter, green filter, whatever filter you want. And what it does is it gives you another level of contrast, because if you look at the sample here, you get some contrast here with these lines going through, and you don't see it in the dark field. So with different Reinberg filters, and the back reflected light gets converted into the color of the filter. So another contrast mechanism, very simple, but it creates beautiful images. And this is the difference between bright field and dark field. With a bright field microscopy, what you see is a lot of light which is being directly coming from the transmitted light source is being cut out of the image in a dark field microscopy setup, and only light scattered at a particular angle is collected. So it gives you a little more contrasting mechanism for some samples. And this comes in very beautifully for some pharmaceutical samples, and I'll give you an example of that. Next up is polarized light microscopy. So in polarized light microscopy, you illuminate with a light source which is polarized at a particular angle. You pass it through the sample, and then you have another polarizer at a different angle, and this is something that you can rotate. Actually, you can rotate the illumination as well and the detection path also. And by rotating that illumination, how the light would interact with a particular mineral and gets polarized in a different direction is something that you'll be able to see. Now, I've given an example of a transmitted, but it could also be reflected light in this particular case. And a fine example of combining polarized light microscopy with Raman spectroscopy is in the field of geology or mineralogy. This is an agate sample. A particular area was selected for imaging. And this is done with a deep UV setup, 2C36 imaging. And when you give colors to the Raman spectra that is acquired from that particular area, the blue, the red, and the green, what you see is a beautiful map. This is a confocal image, even though I'm talking about optical microscopy. But you get a good mineral composition at different locations along with its chemical signature. So you can identify 100%. Okay, with polarized, you can identify, okay, these are the different minerals. But with a Raman spectroscopy combination, you'll be able to see, okay, this mineral is exactly this one, right? Next up, with optical microscopy, contrasting mechanism again, fluorescence microscopy. This is highly used in the field of biology because of its legacy also, and also it gives you the ability of the user to tag the different areas of the cell with different kind of fluoropores, which gives you a better contrast. So in a regular optical microscopy or a phase contrast, you do not see good contrast, but whereas in a fluorescence microscopy, you see some good contrast. And in this case, you have illumination. You have a bandpass filter that only allows 405 nanometer to go through. It passes through the sample. Then you have one more filter, which is collecting the light of the choice. So supposing if you want to collect the red, this would be around 600 nanometers. 600 nanometers. And then it goes to the detector. Now, combining optical microscopy with and confocal is just a matter of changing the principle of data acquisition. That's it. It's not a very unique setup, even though, in terms of the cost of the machine, it appears that it's quite unique. But what you have in this case is, for example, the light sources change from a incoherent light to a coherent light, which would mean a laser. The laser is collimated using a lens, and then it passes through a beam splitter, passes through the sample, and illuminates the sample over here. Gets reflected back, and you have a pinhole to cut out of focus light. So what you're doing is you're trying to increase the resolution by introducing a pinhole on the detection side, so that you do not collect the non-focused lights and you only collect the light which is coming from the center. So that's how you confine it in spatial domain and you increase your resolution. So this is a common example of wide field microscope. You have a laser, you illuminate the complete sample, you collect the complete reflected light back. But with confocal, you want to collect light from a more narrow spatial plane, and you introduce a pinhole just to do that. So this pinhole. So the light which is inside, which is going and focusing here, is out of focus, and the light which is getting focused here is also out of focus. So in focus light is at a particular position only. This gives us the ability. So whereas a wide field microscopy setup shows us the complete area but lacks in resolution in any of the planes, whereas a confocal gives you great resolution but only at one particular plane. And with this, what we can do is then we can take images at different layers. So if I take, for example, this is an embryo cell. We got the sample from IVF clinic, actually. I don't know what kind of an embryo is this, but they wanted to look at the embryo with Raman spectroscopy. So if we take multiple layers of the sample, and then if I generate a three-dimensional data looking at these red particles corresponds to the region here, and the green corresponds to everywhere else. So if I then take, I don't know if I can play this. That's the, okay. So you can recreate these data in three-dimensional, and that gives you a little more, ability to understand your sample structurally. Okay, but also it gives you one more advantage, which is that if you have a spatialized position from where you're collecting the data, and also at one point on the image, you can put this light into a spectrometer. Now the spectrometer will then disperse this and then give you the spectral information. And that spectral information could be fluorescence, it could be photoluminescence, it could be Raman, it could be second harmonic, it could be third harmonic, it could be two photon process, it could also be fluorescence lifetime data. And I'll give you examples of all of those. So this point, now if I remove my pinhole, if this was not there, and I average all the data, then what happens is that I get one single spectra for the complete image. And that, it's not useful because it's a spectra, it's a single spectra, it's not an image information. It doesn't combine all of those things together. Now I'll give you an example of Raman spectroscopy in food science, and this is cheese. Switzerland is Italy, Switzerland, these are known for their cheese. And what they look for is, for example, in this particular case, they've been studying the increase in the whey protein, which is sort of a fatty protein whose content, when it goes up in cheese, increases the quality of the cheese. And this is the Raman spectra, the amide 1 band at 1662, which is related to the whey protein. Now here, when you do a fast Raman scan, you can identify these places. And when you look at the Raman spectra of these green positions, you find, okay, these are associated with whey proteins at 1662. And also, when you go and do again scan and deep, you can recreate these images according to the band that you have selected. So either it's 1662 or 1441 or something like that. You can pick a color for each band and create an image around that. And here you have these examples. For example, the Raman spectra for the whey protein, which is the red, no, not the red, the green region is the whey protein, and then you have associated spectra from other regions, which is fat is red, and then you have the casein matrix is blue. And then you have other examples of these, combining confocal microscopy with optical microscopy. So a wide field image fluorescence would look like this, whereas a confocal fluorescence image would look like this. Then you also have the ability to combine histopathological sections with multiphoton imaging, second harmonic imaging, third harmonic imaging, and sort of a combination of all of those to give you a better insight. Okay, the second harmonic and third harmonic is highly related to the orientation of the sample. For example, fibers in the sample and all those things. You can easily locate them with second harmonic generation and combine them with Raman spectroscopy. You'll be able to see a better information about the sample. Here we have confocal Raman imaging of squashed banana pulp. And here what we see is the blue region corresponds to mostly water. So a lot of water content is there in a banana. Then you have the starch, which is the green one, these particles inside. And then you have the carotenoids, which is the red spectra. Again, continuing with the confocal with second harmonic and photoluminescence, we have Raman image of MOS2, which is here, shift in Raman spectra. Then we have the second harmonic generation image, and it depends highly on crystal orientation. And you can see the defects that you see or interfacing between these different triangles of MOS2 that can be seen here. And that is not visible with the Raman or the PL. And here, PL, we're looking at PL position, and I'll give you a few examples of these also. So change in PL position from 670 nanometers to 710 nanometers. And then we have also in the same setup, everything is still the same. You can do lifetime imaging also from 0.2 nanoseconds of MOS2 flakes to 0.4 nanoseconds variation. So if you see, for example, in the center, you would be around 0.3 nanoseconds. And as you go towards the edges, you start seeing the increase in lifetime on the sample. So there are more examples which are more unique, 1 layer, 2 layer, and you can see more information there. But in this case, this is what we have. Another example of confocal optical combination is this particular example. So we have the optical image of MOS2 flake. This is the AFM image combination. Again, keeping in the theme of correlation microscopy. I'll come to the AFM part later. What we have is a 0.8 nanometer thick flake, and we can see it optically here. We can do Raman imaging at a particular position here. We can do photoluminescence spectra. And then what using the same setup at a higher laser power, you have the ability, because you have a stage that moves in X, Y, and Z, you can make it move in a method that you would prefer. And here, the group has used these laser for ablation on the sample to create these structures. Now, these structure becomes quite interesting at a later point, because when you look at the paper, and this image is from Dr. Kiran Hadra from INST Mohali, that these points can be used as positions of plasmonic enhancement. So if you want to do a surface enhanced Raman spectroscopy, these are the points that can be used for enhancement of the signal. So you can have any types of shapes, so triangular, square, whatever this is. And then coming to geological, for example, exploratory work, it could be petrological exploratory, it could be mineral exploratory, iron ore, and things like that. So this is a group out of Australia, wherein in the peak of China's economic boom, they were importing iron ore from Australia to a large extent. And that's the time when Rio Tinto and all these companies started coming with multiple mines across Australia. And what they wanted to do is that, okay, if I start mining, I should want to make sure that I can get the maximum amount of iron ore or maximum amount of iron from the ore that I collect. So when you have these geological samples which are dug from these mines, if you do Raman imaging at this location, so this is the optical micrograph of that location, you can take the spectra of the carbonate sample. Then you have the hematite, magnetite, and quartz. Hematite and magnetite are common iron ore content minerals, and you can identify. You can in this particular. Sorry. You can identify the amount of hematite and magnetite as a percentage of the image. So if you do multiple set of data, you would be able to come to a conclusion, okay, this is the percentage of the iron ore content that I could be looking at this particular location. So it becomes quite interesting. So the whole gamut, the optical microscopy, the Raman, the lifetime and all those things gives you multitude of information that can be used to analyze data. Now, along with confocal imaging, what you can also do is you can do particle sizing, and this comes in again handy when you look at pharmaceutical samples or microplastics, pollution samples. So if you collect, if you put a filter in the drinking water or sewage water or seawater, you collect the debris which is there, and then you look at what is the amount of pollution that has been happening in these areas and what is the source of that pollution. If you look at major pollutants across the world, it's mostly textile fibers, not microplastics as people perceive it. It's mostly textile fibers. But the major content which is more harmful for us is the microplastics. So this is a technique with which you can do particle sizing and you can identify those particles. For this particular case, it is a pharmaceutical sample, not the microplastics, but there are enough publications on microplastics. So here we have a larger image where we see these particles. We can zoom in and we can see these particles, and then at this particular location we can do spectroscopic imaging so that we can identify the particles, and we can then select these particles and calculate its parameters. So for example, here all these 15, 16 parameters you can calculate, and we can also filter out the particles according to its shape characteristics. For example, in this particular case, we wanted particles that have been selected by circularity, which is greater than 0.9. So most of these particles will remain circular. And this is what we see. So the green ones are the ones which are selected. Now, so particle scouting can be done when you have an optical microscope. Also, with confocal microscopy, if you want to do quantitative analysis, so you have an image in which you have natural rubber, which is the blue part, and the red part as the polypropylene. When you image it, you can calculate the percentage of natural rubber versus the percentage of polypropylene. And when you treat it with something, for example, with hydrogen peroxide or something like that, then you can also check after the process what happens to the concentration of each one of them. So that's sort of combining the optical microscopy along with the confocal setup. And confocal setup could be Raman, PL, fluorescence, lifetime, second, third, harmonic generation, and all. Now, what we want to do is that with confocal setup, what we do is we take all the techniques that we have here and we increase the resolution by introducing a pinhole. Now, if you want to go beyond the optical resolution limit, which is around 300 nanometers, then we have to move towards electron microscopy. Now, electron microscopy is quite interesting. So here, what has been done is that you have an electron beam column. Along with that, parallelly, an optical column has been introduced with the full capability of an optical microscope. So what you have here is a SEM image of a DRAM, random access memory, and then a spectroscopic image overlaid on top of that. I'll explain to you the whole integration aspects here. But so far, electron microscopy integration along with the spectroscopic technique has been little challenging. And what has been done is that in an existing electron beam column, a parabolic mirror has been introduced. Now, with this parabolic mirror, if I have an excitation, if I have a laser source, I can illuminate it like this. It goes to the center where the electron beam is falling. It goes here, then goes out, and here I can put my detectors, any kind of a detector. Now, the main disadvantage is that because it doesn't use a lens, the spot size is in the order of 4 to 5 micron. So in the end, the resolution is more in the order of 5 to 10 microns. And what you see is the discrepancy between the SEM and the spectroscopic technique, because the SEM can resolve really in nanometers, and then you have a few microns. It doesn't really match up to the requirement which is there. And also, because you have introduced a parabolic mirror, it limits the number of secondary detectors that you would want to put on your electron microscopy. It blocks it, right? So the only detector that you have is now the Raman spectroscopic detector. And if you have to use any of the detectors, you have to move it out. Now, another method to do this is that if you have a column for the electron beam, which is separate, and another column for the optical beam. Now here, in this case, once the electron beam measurements are done, you move under the optical microscope, and then you can do white light, all kinds of optical microscopy along with spectroscopic information. The advantages is that it has a resolution which is in the order of 360 nanometers. That's primarily because of the best objective in this class is 100x 0.75 NA. And you can do an imaging of 250 micron by 250 micron, and none of the component of the SEM or the optical microscope have been compromised. So this is what it looks like. You have the optical column here, and then you have the electron beam column here. And I'll give you a few examples of those. This is again the DRAM sample. And when we look at the spectrum data on top of this, and if I draw a line across this and calculate the variation, I can see resolution of 360. Even though the sample is of a higher resolution, it's in the order of around 240 nanometers, but you can't see that because of the resolution that you're limited with an optical microscope. So 360 is something that you can achieve. And then you can apply it to different real world applications. So you have a hamster brain, you can look at the spectral variation across the hamster brain. You have devices, for example, this particular gold, gallium arsenide, you can view them, and also you can identify them with the spectral information. And here, this particular slide is one of my favorites because this is a TiO2 sample. Forget this part, this is incorrect information, it's TiO2. Now, there are two different phases of TiO2 which are present here, and which is the rutile phase and the anatase. And looking at the SEM or the EDS data, we will never be able to tell which one is the rutile, which one is the anatase. Because in EDS, you'll get the Ti and O2 peaks. But when you do Raman spectroscopy, imaging overlaid on top of that, you identify, okay, the red speck, the bigger particles, which is rutile, and the smaller particles, which is the anatase. And this is something that gives you a unique advantage in case of combination of spectroscopy along with scanning electron microscopy. It's highly used in geological samples, and for example, in this case, diorite samples, where you're looking at different mineral composition. And also, because the two columns are separate, the SEM column and the white light column are two separate, you can have complete independence on the detectors that you would want to put on different instruments. So for example, this is a sample of graphene, different layers. And here we can see a zoomed in view of the SEM. When we do Raman spectrum, looking at the spectrum, we can overlay, okay, this is single layer. This is the green one is bilayer, and the red one is multi-layer. You can easily identify those components. Again, graphene on silicon, in this case, you have a graphene flake, and when you do imaging, you can look at the rotation of the flakes and what kind of stacking that is available on those flakes, and you can color code them accordingly, according to the spectra, and then show more information about the graphene than is available just with an SEM spatial information. Now, that was the SEM component, which is combining confocal microscopy and white light microscopy with electron microscopy capabilities, but also you can do all these combinations along scanning probe microscopy combinations also. I haven't detailed the scanning probe microscopy in the number of modes that it has, because that is quite common. And I would want to start with this wonderful example that was done recently. So you have a white light image and you have a AFM. And if you look at and this is an image of Sir C.V. Raman, the founder of the Raman phenomenon. So, and here you have the AFM image, and the AFM height variation is around 20 nanometers. And when you do Raman on the same sample, so you see the correlation optical, AFM, and Raman spectroscopy. It gives you an additional advantage in terms of imaging and also in terms of data analysis. And this is quite simple, because what is hidden in this fact is that the microscope itself was used for generating the feature, because you would use a high power pulse laser that it will move to these locations and ablate the silicon sample to create the structure. And then you move into AFM, and then you move under the Raman to create that image. So it actually not 3 different techniques, but 4 different techniques have been utilized to generate this particular image. Now, the advantages of AFM is, okay, structurally, it's again much higher in terms of Z resolution, is in the order of 1 nanometer, less than 1 nanometer. I would say 0.1 would be a good example. And then in X and Y, depending on the probe size, you can achieve from 2 nanometers all the way up towards 10 nanometers. And it gives you various surface characteristics, topography being the most simple one, but you can also calculate the stiffness of the material. If you have a cantilever that touches the sample, it can identify what is the stiffness, what is the addition of the sample. Those information also can be achieved. And also you can do force resistance curve or sort of indentation. And this is basically the principle of an AFM is revolved around feedback mechanism. So you have a plant output, you take one element of the output and put it into the feedback, and then it goes back into it again. So when the cantilever is scanning over a surface, it sees variations in the surface that is fed back into the feedback loop and given to the piezo scanner to move up and down so that you can measure the sample. And the way this is done with the correlative microscopy perspective is that you mount the cantilever right under the objective that you would want to use. So here, for example, it's a 20x. 20x is where it is mounted. So the whole AFM mechanism is this unit. And then you have the objective in between. And what it does is that you have a magnetically coupled arm on which the cantilever is mounted, and the cantilever is and the feedback element, which is the 9880 feedback laser, is already built inside the objective. So there's no need of alignment or anything, because when you want to move from a from a confocal resolution, which is in the order of 300 nanometers, down to an AFM where the resolution is in the order of a few nanometers, you would want to position it properly so that whole optical integration becomes very necessary. Otherwise, finding the same location becomes a challenging task. So this is how it looks like. So a combination of confocal microscope, an optical microscope, along with the scanning XYZ stage and the feedback mechanism of the system, gives you the ability for optical viewing of the sample. The cantilever is located here, and the feedback is always present in the red circle, which is pre-marked. You don't have to do anything. You just need to bring the cantilever to that position. So, and then it gives you, it gives you structural information. For example, in this case, we have HOPG, single atomic steps in the order of 0.3 nanometers. In this case, the bigger ones would be around 0.7 nanometers. And yeah, you can integrate it with an air setup, and also you can integrate it with the water dipping objective for in liquid imaging. And you can incorporate that with different type of stages that will give you different capabilities. For example, change in temperature and things like that, because change in temperature would be a good factor for polymer blends, rubber, tire industry. And and all these modes are used along with Raman spectroscopy. Usuals are tapping and AC mode, what I've shown, but we also have digital pulse force mode and all these techniques. I won't go into it, but I'll go into this one mode, which is digital pulse force mode a little later. So with topography on collagen fibers, what you can see is if you look at the phase which is gathered along with the in AC mode while performing the scan, you can see these structures on the collagen fibers, and it gives you better spatial information. And again, a few other examples of topography and phase, where in topography you just have the information of the height variation, but in phase you have a material variation also that you can see. Now, for DPFM, what we have is that every tap on the sample is something that we can visualize if we take the coming in of the cantilever and going out in a linear manner. So here the cantilever is coming towards the sample, it jumps into contact, increases in force, goes out, and it requires more energy to come out of the sample, and then it enters a region of these oscillations and then does the same thing again. Now this region shows me addition. This region, the slope of this region gives us the stiffness of the sample. You have the maximum force on the sample. So all these things can then be calculated as a function of the image. So normally you get topography, phase, lateral force, and all those things. But here what we can do is we have the curve at every point. We can do nanomechanical mapping, which is topography, addition, stiffness, viscoelastic properties, slope of addition, and penetration depth of the cantilever under the sample. All can be calculated in their respective units. So you can not only image it, but you can quantify that force as well. And it's as easy with a confocal setup or with an optical setup. The main criteria is it should be as easy to integrate. As you rotate this, you bring in a different objective and you can do any other spectroscopic measurement. And this is sort of a flow chart of how it functions. So you have the AFM, you perform the AFM, you rotate the turret, you perform Raman acquisition, and looking at different places in the sample, you can identify these features. Again, same example on different sample sets. So we have the Raman functionality and the AFM as a combination. Now, I'll quickly skip through this and come to. So here we can see through the objective, we can clearly see the cantilever, we can clearly see the sample, and we can also see at the feedback laser. Now, a fine example, real world application would be looking at graphene samples. You have one layer, you have two layer, and then you have multi-layer here. When you do AFM, you can identify the thickness of the layers, and in this case, it's 0.3 again. And when you rotate the turret, bring in a higher magnification objective, you can do Raman spectroscopy of the same location. And looking at the spectra, you can identify this is single layer, this is monolayer, and this is multi-layer. One more thing with the larger stage AFM is the ability to do staggered imaging, and that when you have a sample which is larger than the ability of your AFM to do imaging, is that you can do individual AFM scans, 1, 2, 3, 4, 5. And you can see here, this is the first image. Then the whole unit is moved to another center location. Around that, one more image is calculated. Then it's moved to another center location, and it matches roughly quite well with the optical image. So you can have staggered AFM images, wherein the area that you want to use for AFM is much larger than the scanner's ability to do imaging on. And this is a fine example. This is a crustaceous insect, or yeah, and it collects calcium carbonates on the chest, and then it slowly internalizes them inside. So when you cut a cross section across the sample here, and you want to do imaging across, so this is the AFM image, but this AFM images are a set of multiple AFM images at different intervals as it goes inside. With the AFM, you find really good structural information, what happens to these calcium carbonate as it goes inside. And when you do Raman imaging across that, what you see is that, okay, that's the Raman spectra. And when you look at the spectrum, you have the CH bending, CH stretching, CaCO3 stretching, and all those things. And you can color code them according to the peaks. And you'll identify here that, okay, on the surface, there is a lot of carbonate signature. And as it goes inside, you have a lot of CH stretching, CH bending information. And the CaCO3 is present throughout, which is sort of a background, which is giving it a yellowish hue, except for this location where you have PO stretching. So this kind of information, along with the structural information, gives you a better insight to your sample. And coming to the last bit of the setup, before we get into it, we would want to see what is the correlation between spot size. Now, all the optical techniques, for example, second harmonic, third harmonic, fluorescence lifetime, Raman spectroscopy, PL, are in the visible domain. So you would say UV, vis, NIR, not more than a micron. For that, all the optics have been refined over a period of couple of centuries, actually. And you have the best in class of optics which are available with high numerical aperture. And that gives us the ability that if I have an visible light source, then if I want to calculate what is the waist diameter of that light source, I can do that by omega 0 actually, which comes to around 377. But this is not what people generally take. They take at a certain distance from the sample, because this is something which is very hard. It's only theoretical. So you go into 2 omega r, and that is a position where the spot size comes to around 333 nanometers. But this doesn't mean that this is the resolution that you can achieve with a confocal setup. You can achieve better resolution because this is only the spot that you're illuminating. So if you have a spot like this with visible UV, vis, NIR all the way up to 800,000 micron, when you go above that, then it becomes a problem. And this is where we are entering the domain of IR imaging and also mass spec. I'll give you a few examples of mass spec. With IR imaging, for example, in this particular case, we have hair samples. Now, the hair samples have been embedded in a resin and microtome. So we're looking inside the hair. And we have the outer layer and the inner layer, which is the cuticle. So as it's going in. So when you do IR imaging, what we're talking about is a light source that is already in the range of 2 to 4 micrometers. Now, optics for these are difficult. I mean, it's not regular optics. So then what happens is the resolution that we can achieve is in the order of tens of micrometers. And this tens of micrometers when compared to Raman spectroscopy. So here, for example, instead of collecting the whole image of the sample, they've done a line scan across the sample. So here you can see the Raman spectra increasing of the cuticle. Then you have the intermediate layer here and the outer layer, which is this part. And this is corresponding IR image. But you can still correlate them. Either in this particular case, what you would do is you would use a low magnification objective where you can achieve a resolution of 2 micrometers or even higher than that. So then you can have a correlation, and this helps because IR spectrum information and Raman spectrum was complementary. What you get in Raman, you don't get in IR, and what you get in IR, you don't get in Raman. So from a perspective of hair care or for a perspective of skin samples, these are quite powerful techniques of combination of IR imaging as well as the Raman spectroscopy. And this is a fine example of colon section from a patient. Looking at, because colon cancer is a major disease factor in, at least in Western world, among human males. So this study was done according in similar light, but what you see is the histological section, and then corresponding different k-means analysis of the IR of the same sample. And then same area you take and you put under Raman spectroscopy, and with cluster analysis, you look at the Raman spectrum. It gives you a little more complementary information. And when this is fed into an artificial intelligence learning platform, wherein you can, okay, this is cancer, this is not cancer, the machine would be able to pick up things much faster than the human in an automated setup. This has not yet been done on a commercial basis, only laboratory basis what I'm taking. But this is an interesting field that if anybody wants to get into. So it can automate this process, because the artificial intelligence has been integrated on MRI, and they have been much 1,000 times better than a human operator. And then finally, with mass spec imaging, in this particular case, what happens is that we have a setup like this in IIT Madras with Dr. Pradeep's lab. What happens is that you have electrospray solvent kind of a tube that hits the sample, ionizes the sample, and then you have a tube of the mass spec that is continuously sucking the ionized sample which is generated and fed into the mass spec. So you, and if you move the stage, you can create an image of that mass spec sample. Along with this, if you integrate an optical microscope on top and you do any spectroscopic technique, you can correlate that sample with mass spec as well as spectroscopic information. And the only issue is that this is in the order of the spot that electrospray, at which electrospray happens, is in the order of 200 micron square all the way up to 400 micron square. So the resolution is very poor, and obviously so, because it doesn't have any optical component or anything like that. It's not an electron beam. It's just a method by which you can sort of eject the sample molecules from the surface of the sample and put it into a mass spec. One great advantage is for mass spec imaging in this particular case would be you can go layer by layer, cutting the layers and then collecting the mass spec image and also the optical image. So that correlation becomes quite interesting if that is something that is of use for your research. Now, before I end, I would like to show an example of the analysis. So here what we have is the spectrum information from a particular location. So if I move on my image at different locations, I will have different spectra. Now, 3 different regions would, in this case, we have 3 different samples. So if I look at the data, you have 3 different types of spectra. So one is the PMMA, one is the PET, and also you have the background, which is glass, and you can see the interference of glass everywhere. So what we can do is, from the complete data set and these 3 samples, if I take it and put it in the software, so sort of a learning mechanism. So the software is sort of a hierarchical technique. So wherein you are telling, these are the materials which are present in my sample, please find them for me. At a later stage, it should be that the system can find it automatically also. So here what we have, the first layer is the PMMA, second layer is PET, and the third layer where there is no deposition of the polymer. And if I extract this information, you get you combine them, and this is what you get. So for the PET, which is the red spectrum, you correspondingly get the red area, the blue spectra, which is PMMA, which is the blue here, and the green one, which is the glass where there's no deposition. You can easily locate this. So this is spectral information in confocal domain. One more great advantage of this is that if I take, for example, a simple sample of a nano indentation on a silicon surface. So, for example, this is looking at the intensity of the nano indentation. And now I can create an image of that indentation by selecting that peak. So if I select the silicon peak, I get the image of the intensity of the peak. But instead of creating the intensity, I can also look at the center of mass of that particular peak. So that means position. So if I select the position of the peak, I get an image which is like this. Now, because the position variation from one point to the other point after indentation doesn't change dramatically, I have to change the color contrast here in order to generate an image that, okay, gives me a better insight. Now, if I plot this on a graph, what we see here from 0, which is dark, all the way up to the brightest point, there's a variation in the spectrum by a factor of 1.2 relative wave numbers only. And you can easily see this. So for example, if you go inside the sample, right click, export, extract graph, you go on top on these bright areas, right click, export, extract graph, and you go somewhere here where there might be a little shift, export graph, and you plot them together. This is the data set that you get. So the graph doesn't show information in the darker region, so that's why it's a little way off. But all the other positions is something that you can see. There's a minor shift in the position of the peak that is visible. Now, within the data set of any particular kind, be it fluorescence or be it second harmonic or third harmonic, there are a multitude of information that you can again extract. So that whole combination of optical microscope, high-end optical microscope with full capability, with the spectral confocal microscope with all spectral information, with an SCM, with an atomic force microscope, with or a scanning probe microscope, with optical profilometers, and all those things gives you a broader view of your sample, and helps in creating a data set that from a machine learning perspective could be very interesting. So on this end, I'll complete my presentation. So I try to keep any marketing material out of it. So in the end, if there was something that I would apologize for that. We had 3 people in India, actually, VTech Direct employees. We have a demo lab in India with all the capabilities except for SCM. And these are the people. Jemmy joined us quite recently in 2019. Since he joined, most of his time has been gone in lockdown and also doing industrial samples on mass manufacturing of graphene and things like that with our industry partners. Amodan is our product manager for VTech products. So all technical discussions, all commercial discussions is something that he handles. Satish Kumar is the product manager for VTech. So he coordinates with Jemmy for all support activities as well as application activities, and he's the lead for pharmaceutical sample analysis. Over the years, he's gained tremendous expertise in pharmaceutical sample analysis. And then that's me. I don't know why I'm in capital letters, that shouldn't be the case, but I'm with VTech since 12 years now, leading the team in India, and we also handle Middle East. And that's it. Thank you. If you have any questions, yes.
Thank you, Mr. Hitesh Mamge. Let us now begin with today's question and answer round. The first question is by Jaime. He wants to ask how to do color imaging of the Raman bands that are observed in sample, that is the method process to modify the micro Raman setup with optical Raman imaging.
Yeah, can you repeat the question again?
How to do color imaging of the Raman bands that are observed in sample. That is the method or process to modify the micro Raman setup with optical Raman imaging one.
Okay, so the ideal factor is that when you're doing imaging using any spectroscopic technique, you will see different spectra from different material on the sample. You can assign a particular color to that spectra, and that gets associated with that. It creates a pseudo color image. It's not real. You give the spectra a color, and that color is then identified in the image in the two-dimensional domain as that particular image. And you can combine multiple spectra to create a combined image of different colors. So again, pseudo color according to the spectrum, not real color.
So the next question is by Prabhavati Nagarajan. She wants to ask what will be the best combination of imaging techniques for viewing the inclusion in diamonds?
Ideally for diamond inclusions, if I can share. Usually you get a petrography stage. With that, you have a light source which is of a different type. I don't have the photograph of that setup right now, but you get a petrography stage in transmission mode, and along with a polarized light microscopy, and then you can integrate, for example, a Raman spectrum setup on top. That would be the ideal combination. It's a very simple combination. It's the best in class optical microscope, polarized light, transmitted light, and Raman spectroscopy on top. And Raman spectroscopy could be just one laser. For diamond, it is fairly simple. Diamond inclusions, it's very simple. Yeah.
So the third question is when we use 532 and 633 nanometer laser, both on zirconia solid sample, some additional peaks are coming in Raman spectrum by 532 nanometer laser.
Okay.
And those peaks are not visible in 633 nanometer laser. So can you please tell us what could be?
So there is a phenomenon, means you have resonance Raman effects also depending upon. So Raman generally is consistent. So use a 266, 532, 785, 1064. The Raman spectra should generally remain the same. But there are certain bands which are, resonant bands with a particular frequency. Those get excited when you are closer to that excitation with that particular laser. And then you would get those bands visible. But I would I'll be a little skeptical with resonance Raman. You should look at the peak characteristics rather than, because if it's a very sharp peak, then there is a leakage, definitely leakage which is happening. But if it is a regular Raman spectra, that time you should consider looking at resonance Raman effects using that particular wavelength.
Sir, one more last question. What is ultra-fast imaging and how it is beneficial for mapping?
So ultra-fast, from my perspective, is a gimmick. Means it's not, it doesn't give the researcher any value addition. Now, let's say, for example, if I'm looking at heart cells, if you isolate them also, they will start beating at a particular frequency. They will beat once in 4 seconds. So now when you're doing that kind of a fast imaging, then probably a fluorescence imaging capability that can do 20 images in 1 second, it will be required, because you're looking at dynamic changes. When there are no dynamic changes, ultra fast imaging by us, by any other person, would be sort of just one more factor that I can put in my brochure rather than any value addition. So if you have a static image, geological sample or a polymer sample that is mostly static, then go for regular imaging, because all the spectroscopic phenomenon. So if I look at, if I illuminate a particular sample with a particular laser, 99% of the light will be reflected, the same laser will be reflected back. Only 1% remains. Now within that 1%, a tiny fraction would be Raman signal or second harmonic or third harmonic. And that tiny portion requires certain amount of time to measure. So if you do ultra fast, you get very slow, you get very weak signal, and that is not something which is desirable. Now there are ways to get into ultra fast when it is required, by getting into electron multiplying CCD cameras and all those other techniques, hardware techniques, which are fairly expensive and also used very occasionally. Yeah.
Thank you, sir. We are really grateful for answering the questions. On behalf of SEV CRNTS, I would like to thank Mr. Himesh Mamge for interesting talk on laser Raman imaging, correlative microscopy technique, a tool for advanced material characterization. I would also like to thank our head, Professor Anil Kotantharial, and our IT team members, Mrs. Nidhi Goyal and Mr. Jagdeep Singh, for their continued support in this webinar series. And last but not the least, I thank all the participants for attending this webinar and making this event successful. A link for the feedback form is shared in the question and answer section. Please do fill the form. Your valuable inputs are important to us. The upcoming talk is on post-translational modification proteomics employing dual and hybrid fragmentation principles coupled to Orbitrap MS. By Dr. Sarvanan Kumar, and the registration link for it is now open on our website. I request you all to join us for the next talk. Once again, thank you for making the webinar successful. Stay healthy and stay safe. Thank you.